Okay, today we're taking on a genuinely massive challenge. How do we actually quantify the immensely complex, incredibly tangled web of global trade? Every single day, ships, planes, and trucks are moving trillions of dollars of goods across borders. But how do economists and policymakers predict the flow of all those goods? How do they know what's going to happen if a new tariff is introduced or a new trade agreement is signed? Well, the answer comes from a rather unexpected place.
Now, I want you to really think about this for a second. What on earth does an apple falling from a tree have to do with billions of dollars in global trade? It sounds like the setup to a strange joke, I know, but it's actually the foundation of one of the most successful economic frameworks ever created.
Believe it or not, the secret is gravity.
Yeah, absolutely. The ultimate tool we have for understanding modern international commerce actually comes straight out of Sir Isaac Newton's 17th century playbook. We literally use the laws of physics to map the flow of the global economy. Okay, let's dive into this. Here's our roadmap for the explainer. First, Newton meets global trade. Then, the math of trade. Next, real-world data challenges, followed by 6 rules for estimates. And finally, translating estimates to policy. We're going to turn this dense academic concept into a totally actionable masterclass. All right, kicking things off with Section 1, Newton meets global trade. So, think about Newton's law of universal gravitation. Objects are pulled together based on their mass and pushed apart by the distance between them, right? Well, the gravity trade model uses that exact same logic. In economics, the countries are the objects. They're pulled together by their economic mass, basically the size of their GDP or overall market size. The bigger the economies, the stronger the gravitational pull to trade with one another. But they're pushed apart by trade frictions. And we're not just talking physical distance here. We're talking tariffs, language barriers, maybe the lack of shared borders. It's actually incredibly intuitive. Large economies that are close to each other, they trade a ton. Small economies separated by oceans, barely at all. Let's see how this builds into deeper economic theory. Moving right along into modern economics, Section 2, the math of trade.
And this brilliantly illustrates why the gravity model is considered the ultimate workhorse of international trade. You see, for decades, economists argued over different micro-foundations for trade. You had Ricardian models focusing on comparative advantage, the Hexter-Ullin framework looking at resource endowments, and models based on monopolistic competition or heterogeneous firms. But what is so amazing here is that all of these completely different theoretical paths actually lead right back to the exact same place, the Armington CES gravity model. It's honestly the great unifier of trade math. But if we want to use this math correctly, we have to grasp this crucial and honestly often misunderstood concept: multilateral resistance. Let's translate that heavy econometric jargon into plain English, shall we? It simply means that trade between two countries doesn't just depend on the bilateral barriers between them, it depends on their relative position and their alternatives in the entire global market. So, if two countries are physically isolated from the rest of the world, like Australia and New Zealand, they're going to trade a whole lot more with each other than two equally distant countries situated smack in the middle of Europe. Why? Simply because those European countries have incredibly easy access to dozens of other neighboring markets. This idea is so absolutely vital that economists Baldwin and Taglioni literally coined a phrase for ignoring it. Failing to control for multilateral resistances is committing the gold medal mistake. It's pretty much the ultimate statistical sin in empirical trade analysis. If you forget to include this invisible metric of global market access, all of your bilateral trade data is going to be fundamentally biased. Now, while the theory is elegant, the real-world data policymakers have to use is a total mess. Section 3, Real-World Data Challenges.
Let's face it, data scientists deal with a rapid-fire list of mathematical headaches when looking at global trade. First off, like we just said, multilateral resistances are invisible. You can't just download a spreadsheet of them. Second, trade policies are endogenous. Countries naturally sign free trade agreements with the nations they already trade heavily with, creating a massive chicken and egg causality problem. Third, heteroscedasticity. Basically, your predictions get wildly more unpredictable when dealing with massive economies compared to small ones, which completely skews traditional modeling. And finally, the most notorious problem of all, the dreaded zero trade flows.
I want to role play with you for a second. Imagine you're a data scientist. You're looking at a trade data set between two really niche sectors in two small countries. There's no trade happening. The value is literally just zero. Now, historically, to estimate the gravity model, economists use log linearized equations. But remember your high school math? The logarithm of zero is mathematically undefined. It literally breaks the model completely. So traditionally, software would just drop those zero observations entirely, essentially throwing away incredibly valuable data about exactly why two countries aren't trading.
So the crucial point is you really can't just fake the math. For years, a super convenient trick was just plugging in a tiny, completely arbitrary number like 0.0001 to replace the zeros just so the logarithms would work. But doing that is completely theoretically inconsistent. It makes your results totally dependent on units of measurement and utterly destroys the economic elasticities you're trying to figure out in the first place. You're basically corrupting the entire dataset. So how do we fix this? Welcome to the masterclass portion of the explainer. Section 4, 6 rules for estimates. If you're taking notes, this is absolutely the checklist to screenshot. To obtain reliable partial equilibrium estimates, you've got to follow these 6 rules from the latest literature. 1. Use panel data for better efficiency. 2. Use interval data. We're talking 3, 4, or 5-year gaps, not consecutive years. 3. Include intranational trade, meaning domestic trade inside a country's own borders. 4. Use directional fixed effects to capture those invisible multilateral resistances. 5. Use pair fixed effects to solve that tricky chicken and egg endogeneity problem of trade policies. And 6. Use the PPML estimator. Let's look a bit closer at that last one. This is kind of the climax of the methodology right here. On one side, we have the old way, log linear OLS regression. It's biased, it's inconsistent when faced with heteroscedasticity, and it crumbles the second it sees a zero. On the other side is the modern savior, the Poisson pseudo-maximum likelihood, or PPML estimator. Because it calculates the gravity model in its multiplicative form rather than its logarithmic form, it naturally accounts for heteroscedasticity. And miraculously, it handles zero trade flows perfectly without needing any fake numbers. It completely bridges the gap between pure theory and messy reality. All right, let's bring it all home and apply this to the real world. Section 5, translating estimates to policy.
Now, what's really interesting about this slide is how these rigid econometric rules actually reflect human behavior. Think about it. Why do we use 3, 4, or 5-year intervals? Well, because economies need time to actually adjust. If a tariff drops today, supply chains don't magically move tomorrow. You just can't measure policy changes year by year. Why include international trade? Because to understand how an international border affects trade, you really need a baseline of how much citizens trade within their own border first. And finally, you absolutely must match the policy to the specific sector. Tariffs on agriculture behave totally differently than regulations on digital services.
By combining all these rules, panel data, fixed effects, the PPML estimator, we end up constructing a perfectly tuned gravity model. And here's why this matters so much. It empowers data analysts to measure the true, unbiased ripple effects of tariffs, borders, and regional trade agreements. We can simulate counterfactuals. We can map exactly how a policy change in one corner of the globe is going to shift the gravitational pull of economies everywhere else. So, I'm going to leave you with this final, genuinely provocative thought. Next time you're looking at the news, think about this. If a newly signed trade agreement acts as a massive gravitational shift today, how will its ripples reshape your local economy tomorrow? Thanks to the structural gravity model, we don't have to guess the answer anymore. We can actually calculate it. Thank you so much for joining me for this explainer. I hope this helps you see the forces shaping our global world in an entirely new light.